Hello everyone, my name is Artem Shelostom and this is my lab report for Lab 3 Black Hole. The purpose of this lab was to analyze motion of objects in the vicinity of a black hole to find mass and exit velocity. We found mass using a star orbiting it, and as we can see in the picture on the left, the mass turned out to be 1.6 times 10 to the 34th kilograms, and find an exit velocity for a ship orbiting the black hole with a planet next to it as well. So the laws used here are Newton's second and the universal gravitation. Newton's second law states that the force acting on an object is equal to the mass of said object multiplied by its acceleration, so F net equals to ma. And the law of universal gravitation means that the force of gravitation is g times m of the other object divided by the magnitude of the distance between them squared times the direction of said distance times minus 1. And then F net is sum of all forces and dp dt, according to Newton's second law. F net parallel is the magnitude of the net force times the direction of the momentum, and the perpendicular is just F net minus F net parallel. So this data can be used to estimate acceleration and speed of the object. The procedure was to model a star orbiting a randomly generated black hole using my email as a seed and finding mass of said black hole from the law of universal gravitation, and then using this mass to simulate a spaceship and planet orbiting it to find some exit velocity for the spaceship. So the initial conditions in part 1 were the random velocity and position of the star. Mass of the star was 2 times the 10 to the 30th kilograms. The system is just the star and the black hole, and the time steps was 1 day. For part 2, the initial velocity of the planet was still random based on the black hole. Initial position was 1 times 10 to the 10th, and the initial velocity of the ship I found is negative 2 times 10 to the 7th and 1 times 10 to the 7th, 0 meters per second. The position is just the position of the planet, but 1 times 10 to the 8th in the positive y direction. Mass of the black hole was calculated in part 1. Mass of the planet is 9 times 10 to the 28th kilogram, and mass of the ship is 7 times 10 to the 10th kilogram. So in part 1, firstly I changed the seed, then I inputted the mass of the star in delta t, and then I used the fact that momentum is speed times mass to find the initial and final momentum, find the delta v and delta p as the final minus initial value of each of them. dp dt is just the change in momentum divided by change in time. F net is dp dt according to Newton's second law. And I calculate p hat, and the magnitude of p dt, it's just the magnitude of p final minus initial divided by delta t. And to find the projection on the parallel component of dp dt, you just multiply it by the direction vector. So F net parallel is just dp dt parallel, also from Newton's second law, and perpendicular is just like the net minus the parallel component. Then you find the mass of the black hole from the law of universal gravitation, and find the average mass of the black hole to calculate it from all the different masses which will be calculated throughout the experiment. So the result was that the mass of a black hole is 1.6 times 10 to the 34th, as mentioned previously, and the star makes full orbits around the black hole. In part 2, I inputted the mass, and I found the initial velocity, which would let it exit, and then I found the distances as the difference of position vectors, and net forces as just sums of forces from the law of universal gravitation. And then I updated position and velocity using position and velocity update formulas. The results were that the spaceship flew away from the system, and in 60 minutes it did not return back. So possible sources of error in part 1 was that continuous data such as the force, the speed of the star, and its position were treated as discrete. They were generated with concrete time steps, and these time steps were 1 day, which is pretty large. So there was like really big variance with the mass of the black hole. And in part 2, this is not the only initial velocity, and there is no information how the spaceship would behave after a long period of time. So how is the net force different from changing momentum for the first part? It is the same thing, but dp dt is what we use to calculate measure force, because you cannot directly compute a force. So dp dt is a more computable value because it's just composed of the mass of the object, its speed, and a time interval. If we wanted the spaceship to orbit the black hole, a speed which is similar to the planet would be required, in my opinion, because the planet is orbiting the black hole. So the same direction is needed, but it has to be a bit bigger, because if it's the same or smaller, it would just get influenced by the planet's gravitational field. So you can see below the results of running v-ship times is equal to v-planet times 1.1. It does not make a full orbit in the time which the simulation allows, but it looks like it would, because it makes a half circle around the black hole. Thank you for your attention.